Hello everyone. Let's analyze. So in previous lectures we've defined what the derivative is for a function that maps vectors in Rm to vectors in Rn. And a key point is that the derivative of a function that maps a vector in Rm to a vector in Rn, if I take the derivative and evaluate it at a single point x0, then I have a linear operator from Rm to Rn, which is equivalent, given a choice of bases, to having a matrix of size n by m. And the analogy for the one-dimensional function, the calculus 1 style function, is that the derivative of a function evaluated at a single point is a number, and a number is equivalent to a linear operator from R to R. Right, that number specifically is the slope. Of course, in the previous lecture, we saw how the numbers in the n by m matrix, representing the derivative of f at x0, is an array of slopes of the different entries of f and the different cardinal directions given a canonical basis. So these properties that we see here should be pretty familiar to you. The idea that the derivative can be distributed over a linear combination of differentiable functions, right? That's a familiar property. If n is 1, the derivative of f times g, and of course f times g there is just a product of two numbers because the output of f and g is a real number. The derivative of f times g is given by the product rule. Again, if n is 1, right, the dimension of the codomain, and g of x0 is non-zero, then if f and g are differentiable, so is the quotient f divided by g, also differentiable at x0. And the derivative is given by the quotient rule, which is the quotient rule that we're familiar with. Low d high minus high d low over low low. I still remember that. So the proof of these three properties follow exactly in line with the analogous proof in real analysis 1 when everything was scalar valued. And it would be a good exercise to repeat those proofs for these properties, but we won't prove it here. What we will prove is the chain rule. Even though the proof is actually fairly similar to the proof in one dimension, it is a good idea to go through the proof and see how we might adapt it to the multidimensional space. So again, the chain rule gives a formula for the derivative of a composition of functions, in this case g and f. All right, so f maps an open subset of Rm to Rn. The image of f is contained in the domain of g because g has to be defined on f of x and u. So long as f is differentiable at x0 and g is differentiable at f of x0, because I'm composing g and f, then the composition is differentiable at x0. And just so that we're clear, when I say the composition of g and f at x0, what I mean is g of f of x0. So the output of f is the input of g. And the derivative is given by the chain rule that we're familiar with. Of course, if m, n, and k were all 1, then this would just be the traditional chain rule we've seen since calculus 1. So let's prove this statement. Now our goal is to show that the composition, which we'll call h, is differentiable at x0, and that the derivative is given by the chain rule formula. Well, remember, the derivative of f evaluated at a single point x0 is a linear operator from Rm to Rn, which is equivalent to a matrix of size n by m. So we're going to call that matrix AF. Similarly, we're going to call AG the matrix given by computing the derivative of g and evaluating at f of x0. And AH is the product of AG and AF. Now, if my chain rule is correct, then AH should be the matrix representing the derivative of h at x naught. This ought to equal this. Now, we accomplish our goal if I can show that AH satisfies the definition of the derivative, which is h of x minus the tangent function divided by x minus x naught is 0, and the limit as x approaches x naught. So, as always, let epsilon be positive, and let's consider the numerator in my goal limit statement, right? So this term here. Well, h of x, remember, is g of f of x. H of x naught is g of f of x naught. And AH is the product of AG and AF. So let's add 0 to that, but with style and substance and in red, in the form of adding AG times the change in f and subtracting AG times the change in f. So by adding the 0 gives me a convenient place to cut and make use of the triangle inequality. This term has an AG in both terms, and I can factor it out. And if I look at what's inside of this parentheses, I have the numerator for the derivative statement of f. And of course, we know f is differentiable. Similarly, over here, I have the numerator of the differentiability statement of g. And we know that g is differentiable at f of x naught. Now, we know that f is differentiable. So we know that if we take the limit as x approaches x naught of f of x minus its tangent function, divided by x minus x naught, I get 0. Right? Because that's the definition of the derivative. So of course, we know what that limit means. Right? We've all taken rule analysis 1. A limit for any epsilon, and we have an epsilon. There exists a delta. We'll call it delta 1 because, well, we're going to have a handful of deltas. So that the open ball centered at x naught with a radius of delta 1 is contained in U. Now, how do I know such a ball is contained in U? Well, because U is open and x naught is in U. So for every x naught, there's got to be an open ball with a positive radius contained inside of U. And if x is within delta 1 of x naught, but not equal to x naught, then this difference, right, whose limit is 0, is as small as I like, or as small as I like, however small that I like, there's a delta 1 that'll get me there. Now, why this form? Why does it look like this? Well, we can kind of look ahead and see that I want this, when I divide by x minus x naught, to be less than epsilon. So I need this, when divided by x minus x naught, to be less than epsilon. And same thing with this. This divided by x minus x naught has to be less than, or the sum has to be less than epsilon, so each of these have to be less than half of epsilon. Right, there's this norm of AG factored out. Remember, the norm of a matrix is the max norm of the matrix times the unit vector. And that's why I can factor it out and get this less than or equal to. So I need to be able to cancel this. So I have epsilon over 2 times the norm of AG plus 1. Now, why this plus 1? Why not just the norm of AG? Right, this norm of AG will cancel with this, and I'll get epsilon over 2, and I call it a day. Well, because the norm of AG might be 0, right? It could be that the derivative is 0 when I take the derivative of g at f of x naught, and that's what this matrix is. Right, so just in case this is 0, this prevents me from having to divide by 0, which not even Chuck Norris can do. Right, and for the same reasoning, because g is differentiable at f of x naught, there exists another delta 2, so that the ball centered at f of x naught with a radius of delta 2 is contained in the open subset V. Right? Why? Again, because V is open. And because it's open, and f of x naught is in V, there's got to be a ball centered at f of x naught with a positive radius contained in V. Furthermore, if the difference between y and f of x naught is less than delta 2, and y is not f of x naught, then this term is less than any positive number. Or given any positive number, there's a delta 2 that'll get me there. Because this is the statement of differentiability at f of x naught. Right, you notice the subtlety of this y here because, right, any y that's within, right, a delta 2 radius of f of x naught, any y that's close enough but not equal to f of x naught, then my derivative rule is arbitrarily small. Now, what's epsilon tilde, you ask? Well, I'm glad you asked. It's to be determined. It's whatever we need it to be, right? Whatever positive number we need it to be, there's a delta 2 that'll get us there, because that's what a limit being 0 means. And that limit is 0 by definition of differentiability, which we've assumed to be true for g at f of x naught. So I can multiply this term on both sides by the norm of y minus f of x naught. That gives me this term. Okay, now I can make this as close as I like, because since f is differentiable at x naught, it's continuous at x naught. Right? So long as this y is some f of x. And of course, this y is some f of x because y is contained in this ball. This ball is contained in V, and, well, V contains the image of f. So since f is differentiable at x naught, it's continuous at x naught, there exists a delta 3 such that this ball centered at x naught with the radius delta 3 is contained in U, again because U is open. And if x is within delta 3 of x naught, f of x minus f of x naught is less than or equal to, actually this should be a strict inequality, is less than delta 2. There, it's fixed. The magic of the internet. So it's a strict inequality, which means f of x is within the open ball centered at f of x naught with radius delta 2. So if x minus x naught is small enough that this is assured, and the epsilon over 2 times the norm of ag plus 1 is also assured, which means this difference has to be less than delta 1 and delta 3, which is why delta is defined to be whichever of these is smallest. Then, well, let's recall I've bounded this numerator by this plus this. This term we said is less than epsilon over 2 times this plus 1. And this, well, so long as f of x satisfies the condition that y satisfies, I've got a bound for that as well. So when I divide by x minus x naught, this first term is less than epsilon. F of x is playing the role of y minus f of x naught over x minus x naught. And of course, this term we know is less than epsilon over 2 times the norm of ag. Again, plus 1 just in case the norm of ag is 0. Now notice the norm of ag divided by the norm of ag plus 1, right? That's less than 1. So I just get epsilon over 2. To this term here, to make it as small as I like, I'm going to add and subtract 0. I'm going to add 0 by adding, subtracting the derivative of f at x naught times x minus x naught. Right? I can then use a triangle inequality to split that. And if I look at this term divided by this, right, that's just my difference quotient for the derivative of f, which I know I can make as small as I like, and I've already made it this small. and the norm of AF times this times x minus x naught divided by the norm of x minus x naught, that's less than or equal to the norm of AF times epsilon tilde. So the second term I've made half of epsilon. Well, I can make this half of epsilon, right? Because epsilon tilde is a value to be determined. So it's whatever value I need it to be so that I get my result. What does epsilon tilde have to be? Well, it has to be epsilon over 2 times the reciprocal of this. And if it is, I get epsilon, and my difference quotient is less than epsilon, which means I've shown that h is differentiable at x naught, and the derivative of h at x naught is given by AH, where AH is constructed by the formula given in the chain rule. So we've proven our result. So let's work out an example. Suppose I have a function f that maps vectors in R3 to vectors in R2, and I have a function g that maps vectors in R2 to vectors in R3. So then the composition of g and f maps, well, vectors in R3 to vectors in R3, because the domain of f is R3 and the codomain of g is R3. Of course, it passes through R2 on the way. So let's compute the derivative of h by computing h and taking a derivative, and using the chain rule, and confirm that, well, in fact, it works. So we'll consider computing the derivative at x naught. Of course, I'll need to compute the derivative of g at f of x naught, which is 3, negative 4. So h is the composition, right? So it's g evaluated at f of x. So it's, instead of 2x1 squared, it's 2f1 squared times f2. Right? Instead of x1 plus x2, it's f1 plus f2. Instead of x2 here, it's f2. Because I'm evaluating g not at x, but at f. And if I plug in what f1 is equal to and what f2 is equal to, then I get this expression. So I can compute all the derivatives, right? The formula for the derivative is given by the Jacobian matrix. So I can take all of my partial derivatives. But if I take all 3 partial derivatives of this, I get the top row. If I take all 3 different partial derivatives of this, I get the second row. And if I take the 3 different partial derivatives of this expression, I get the last row. Another way to think about it is, if I isolate this function and compute its gradient, the transpose of that gradient is the top row. The transpose of the gradient of this function is the second row. And the transpose of the gradient of this third function is the third row. So notice, right, that's quite a bit, right? First I have to compute g of f, then evaluate what that is, and then take my 3 derivatives. Now if I evaluate at 1, negative 1, 2, I get this expression. But I also could have got that matrix by taking the derivative of g at f of x naught, which is 3, negative 4, times the derivative of f at x naught, 1, negative 1, 2, right? 1, negative 1, 2. So the derivative of f, right, take the derivative of this expression. That is, take the gradient of this first function, transpose, 1, 0, 1. Take the gradient of this function, transpose, I get this expression. Evaluate at x naught, I get this matrix. Similarly for g, take the derivative of g, evaluate at f of x naught, which is the vector 3, negative 4, I get this. Now, if I multiply this by this on the right, I get that. And right, I would encourage you to check that that's right. It is right, by the way. You should check. I mean, it is right, but I mean, you might as well check. Right? So this matrix times this on the right equals this. Now, suppose I don't want the full Jacobian of h, right? Suppose I don't want to go full Jacobi. I only want the partial derivative of the ith entry of h in the direction of the jth coordinate. Right? So I just want a single partial derivative. Well, by using the linear algebra and the chain rule, it's equal to this inner product, right? It's equal to the inner product of the gradient of gi and the gradient of, the derivative of f with respect to that single variable xj. Right, so this is a vector, right? It's the derivative of every entry of f with respect to the same coordinate xj. So this vector dot product with this vector. That dot product gives me this partial derivative. Now, the next property of the derivative we're going to discuss is the mean value theorem. But in order to discuss the mean value theorem in multiple dimensions, we need to understand the concept of intervals in multiple dimensions. Essentially, when I'm talking about an interval of two vectors in Rn, well, I can think of each vector as a coordinate. And I can think of the line segment between these two vectors as essentially the line connecting these two coordinates. If the two coordinates are contained on the line, I have a closed interval. If they're not, I have an open interval. And so that line can essentially be described as a convex combination. A convex combination is a linear combination where the coefficients sum to 1. Right, so alpha plus 1 minus alpha obviously sum to 1. Right, a scaling of v plus a scaling of u, that's a linear combination. So that's what a convex combination is. By taking a linear combination with coefficients that sum to 1, I'm guaranteed to be on the line between u and v. And by the way, a subset is called a convex subset if for any two entries in u, the convex combination is contained in u. Okay, now we can give the mean value theorem. So let f map an open subset u of Rm to Rn. Suppose it's differentiable on all of u, this open subset. Then for any closed interval, remember this closed interval is the line connecting the two coordinates x to y, including x and y. For any interval contained in u, well, if n is 1, there exists a c along that open line for which f of y minus f of x is the derivative of f at c. Right, of course, if n is 1, this is just the gradient of f transpose, evaluated at c, times that difference y minus x. Right, so we can think of this as almost like a directional derivative. Right, essentially it's the slope in the y minus x direction. And if n is not 1, but greater than 1, then essentially I can make this statement for each entry of f. Right, and in other words, because f is vector valued, there's a first entry, a second entry, a third entry, a nth entry. For each of those entries, this statement is true. Now, we'll go through the proof in a bit of a sketch. The result essentially follows by applying the one-dimensional mean value theorem repeatedly to the function h of alpha, where h of alpha is f of alpha v plus 1 minus alpha u. Now, this is true for each entry of f, right? So it's true for j equals 1 through n. But because if n is greater than 1, the mean value theorem is just a repetition of the mean value theorem when n is 1, just applied to each entry of f. So in some sense, we can just kind of disregard this j and consider this function. So notice, right, alpha is a number, right? It's a number between 0 and 1, and h is a number, right? So h of alpha is just a real function of a real variable. It's a calculus 1 style function, right? It passes through a vector, right? This input here is vector valued, but right, if I treat this as a black box, in goes a number alpha, out comes a number h. So I can apply the one-dimensional mean value theorem to that. The one-dimensional mean value theorem tells me that the difference in h when alpha is 0 and when alpha is 1, in other words, the difference between f of v and f of u, well, f of v is h of 1, because if alpha is 1, right, I just get 1 times v plus 0 times u. So I get this expression, minus h of 0, because if h of 0 is f of u, of course, divided by 1. So that equals h prime of gamma, where gamma is some number between, strictly between 0 and 1. Now, what is h prime of gamma? Well, h prime of gamma can be computed using the chain rule. The chain rule says it's equal to this expression. Right, gamma is some number between 0 and 1, so this is this convex combination is some vector on the line between u and v, and so we'll call that vector Cj. Right, j to correspond to this j. Well, again, if I disregard my j's, then I have exactly this statement, and if I add my j's, I have exactly this statement. Right, so long as this is the c on the open interval. And how do I know that this is on the open interval? Because this gamma, which is guaranteed to exist by the one-dimensional mean value theorem, is in the open interval 0 to 1. So we've proven our result. And that's it for today.